Okay, so it's time for discussion 8-1, gas relationships. This is one of two lessons in Unit 8. It's going to be short and sweet. Okay, so in this unit, we're going to do a lot of math. And we're going to do a lot of calculations concerning gas behavior. Now we're going to look at how the pressure of a gas changes as we change the volume of the container or the temperature that the gas is in. Right, so whenever we're going to use temperature in these equations, we have to use the Kelvin scale. Kelvin scale must be used. So if you're ever given a temperature in Celsius, the first thing you need to do is convert it into Kelvin. So let's talk about this scale. 0 Kelvin is known as absolute zero. And absolute zero is the temperature at which all molecular motion stops. And that temperature is negative 273 degrees Celsius. Now, it's actually kind of cool to think about. Kelvin is called the absolute scale because of absolute zero. Now, temperature, we know, is just a measure of the kinetic energy of the particles of the sample. The faster the particles are moving, the higher their temperature is. So when the particles stop moving altogether, you have an absence of temperature, zero temperature. And that's why Kelvin is called the absolute scale, because you literally cannot get any colder than absolute zero. So the Kelvin scale is intricately connected to the Celsius scale. 1 degree Celsius is equal to 1 Kelvin. Now, because 0 Kelvin is negative 273 degrees Celsius, if we want to find the Kelvin temperature of a sample, we have to take the number of degrees Celsius and add the number 273. So 20 degrees Celsius would be 293 Kelvin. Okay, so I want you to practice converting these temperature values into Kelvin. All right, so take a moment and pause your video and see if you can't do that. Okay, so 25 degrees Celsius. To find the Kelvin temperature, we have to take those degrees C and add it to 273. So 25 degrees Celsius is 298 Kelvin. Notice I'm not using a degree symbol for Kelvin. When we write the Kelvin temperature unit, we just write the capital K. So 100 degrees Celsius. Well, same thing. If we want the Kelvin, we have to take that 100 and add 273 to it. So 100 degrees Celsius is 373 Kelvin. Now for 0 degrees Celsius, if we want to convert to Kelvin, we're going to add 273. So 0 Celsius is 273 Kelvin. So remember, every degree in the Celsius scale is a degree in the Kelvin scale, only the Kelvin scale differs because it starts at negative 273 Celsius. Okay, so we describe the behavior of gases with something called kinetic molecular theory. And you may see this abbreviated as KMT. All right, so kinetic molecular theory contains 4 main postulates. 1, that gas particles are in constant motion, and they move in straight lines, in random directions. So if you have a balloon that's filled with gas, all the molecules or atoms of gas in that balloon are all zipping around at high speed in straight lines in random directions. Now, the speed of the gas particles, the kinetic energy of the gas particles, is only dependent on the Kelvin temperature. So again, if we heat up the sample, the particles will be moving faster. If we slow down the particles, they'll be moving slower. Third, gas particles undergo fully elastic collisions. Now this sounds very, very sciencey, But really all it means is when they bounce off from each other, they don't stick in any way. They bounce off from each other and do not lose any energy when they bounce into each other. Imagine you had a bouncy ball, and every time you bounced that bouncy ball on the floor, it came exactly back up to the level that you dropped it. And it would do that forever and ever and ever. Now we know in reality, when you drop a bouncy ball on the ground, every time it bounces, it will come up to a lower level. And it will keep going to a lower level until it bounces to the ground and stops bouncing. So a bouncy ball does not undergo elastic collisions. Gas particles do. And there is no force of attraction between gas particles. Right? So when they bounce into each other, there's no kind of attraction between each other. They just bounce off from each other and keep going about their day. And we can talk about this later to see how kinetic molecular theory actually explains how gases behave in our world. Okay, so pressure. Pressure is a force per unit area caused by the collision of gas particles. Collision. I don't know if that's spelled right, but that's okay. The collision of gas particles with the walls of the container the gas is in. So that force we feel as pressure on our ears, for instance, when we're in an airplane, is caused by the gas particles in the airplane as it's pressurized hitting our ears. Okay? Now, the more collisions that there are, the greater the pressure will be. All right, so measuring pressure. All right, so pressure has several different units. These are the most common that you will see. The first is torr, and you know we saw torr on our Unit 7 test. Torr is actually millimeters of mercury, and that seems like a strange unit. But when you understand how a barometer works, it makes perfect sense. This device here is known as a barometer, and you've probably heard this from watching the weather report. Now, the barometer is basically a bowl or a dish filled with mercury. Right? Now, we have pressure always coming from the atmosphere, and that's called atmospheric pressure. And the atmospheric pressure is just the force of pressure that we feel caused by the Earth's atmosphere. So the atmospheric pressure is always pushing down on that pool of mercury. And in that pool of mercury, is an upturned test tube, if you will, kind of like a thermometer tube. And as the pressure increases on the mercury in the dish, it forces the mercury in the tube up higher. Now, the lines on this tube are in millimeters, and that is where the unit millimeters of mercury comes from. Okay. Now, we have what's known as standard pressure. And these three values here are pressure in standard pressure. And this is just the pressure we feel on any given day while we're outside. Right? So our other two units of pressure are atmospheres or kilopascals. Now, at standard pressure, the pressure will be 101.3 kilopascals. It will also be 1 atmosphere, which makes sense because we have 1 atmosphere over top of us, or 760 torr. And if you look at our barometer here, you see that it is measuring 760 millimeters of mercury. So this barometer that's in our illustration is measuring atmospheric pressure. All right, so if you're in class, we'll do a cool little demonstration concerning atmospheric pressure. Okay, so there's 3 factors that can affect pressure of a system, and there's 3 ways we can change it. 1, we can change the volume of the container that the gas is in. The other thing we could do is change the temperature of the sample. Finally, if our container has rigid walls, in other words, walls that are not flexible, we could add more gas, and that would cause the pressure to increase. Now, as we go, I want you to think about this in terms of collisions with the walls of the container. If we add more gas, there's going to be more gas particles in the container, so we're going to get more collisions with the walls of the container simply because there's more particles. Right, so that is how we're going to increase the pressure, by adding more gas. So let's look at pressure and volume. Now I want you to think about this because this is common sense. Right? As the volume of a container decreases, what do you suppose would happen to the pressure inside the container? Think about that. You've got a balloon and you squeeze the balloon. What is going to happen to the pressure inside that balloon? Think about it for a second and then come back to the video. All right, so if you decrease the volume, the pressure inside will increase again. If you have the same number of gas particles in a smaller space, then you are going to get more collisions with the walls of the container and higher pressure. All right, so this is what's known as an inverse relationship. As one factor decreases, the other will increase by the same factor. Now, if we graphed an inverse relationship, we have our y-axis and we have our x-axis. The graph would look like this. Now, that is the curve of y equals 1 over x. I don't know if you remember that. Right? So, if it's an inverse relationship, if the volume is doubled, that is an increase in volume, so the pressure will be cut in half. It'll be halved. If the volume is cut in half, then the opposite will happen to the pressure. If the volume is cut in half, then the pressure will double. Finally, if the volume is tripled, the pressure will go to 1/3 of its original amount. Marker's freaking out. All right, now I just want to note, that says pressure must always be in liters. Silly me. Volume must always be in liters in order for this relationship to be true. So we'll practice in class, but if you're given milliliters, you have to convert that value into liters. All right, so Boyles Law is just the mathematical relationship between pressure and volume. And here it is. P1 V1 equals P2 times V2. So we have an initial pressure and an initial volume. Right? If we have a second pressure, we could calculate the second volume. So essentially what we have here is an algebraic expression, an equation. You're going to be given 3 of the factors and asked to solve for the third. So let's look at an example. It says you have 1 atmosphere of gas in a 10-liter container. What will the new volume be if the pressure is increased to 3 atmospheres? Now, this unit is 95% these kind of mathematical relationships and plugging numbers into an equation. So when you solve these problems, I want to see no laziness. We're going to list out our units every time so that we can plug them in appropriately. So it says we have this 1 atmosphere of pressure of gas in a 10-liter container. So you have to know that volume is the liters and atmospheres is the pressure. So I'm going to say that V1, the initial volume, is 10 liters. Right? The initial pressure of that sample of gas is 1 atmosphere. It then tells us that we're going to change the pressure, so P2, to 3 atmospheres. So then it wants to know what is the new volume. So we'll call V2X. Now, we know from the previous slide that if you triple the pressure, you're going to cut the volume down to 1/3. So before I even perform this calculation, I would expect my new volume to be about 3.3 liters. So let's go ahead and plug into our equation. P1 is 1 times V1, which is 10, equals P2, which is 3, times X. So X is going to be 10 divided by 3, which is 3.3. And we're looking for volume, so our answer has a unit of liters. Okay, so let's look at the relationship between temperature and pressure. Now again, this is kind of common sense. If the temperature of a gas sample increases, then what would you expect to happen to the pressure inside? Take a moment and think about it. Come back to the video. So if you increase the temperature, you're going to also increase the pressure. Think about leaving an unopened bag of potato chips in a hot car. When you come back, the bag looks like it's been inflated like a balloon. That's because the pressure of the gas inside is increasing. Or the pressure caused by the gas, I should say. So this is a direct relationship. As one factor changes, the other changes right along with it. So here we again have our XY plot. If I was going to plot a direct relationship, the line looks like this. And the graph is Y equals X. So if I have some hash marks on this graph, let's say I'm starting at the origin. If I move Y up to 1, then X goes to 1 as well. If I move Y up to 2, then X goes to 2 as well. As one changes, the other changes right along with it. So if you double the temperature, the pressure will also double. Now, I think it's important to note, if you double the Kelvin temperature, the pressure will double. If the Kelvin temperature is cut in half, pressure is cut in half. If the temperature is tripled, pressure is tripled. So this. Okay, so Gay-Lussac's law, haha, have your laugh, is the mathematical relationship between temperature and pressure. Now, since pressure and temperature is a direct relationship, Gay-Lussac's law is P1 over T1 equals P2 over T2. Now, when we solve pressure and temperature problems, we do it in exactly the same way. So, as we did with Boyles Law, excuse me. So the question says, you have a sample of gas at a pressure of 570 torr and a temperature of 27 degrees Celsius. What will the new pressure be if the temperature is increased, to 50 degrees C? So I'm going to go ahead and label my variables. It tells me that the initial pressure is 570 torr. And it tells us that the temperature of that sample is 27 degrees Celsius. Now, every time you do your problems, you have to ask yourself, are the numbers given to me okay, or do I gotta tweak them a little bit? Well, we know that degrees Celsius must be converted to Kelvin for all of these problems. So to convert Celsius to Kelvin, we add 273, and that tells us that T1 is 300 Kelvin. It then tells us that the new temperature is going to be 50 degrees. So T2 is going to be 50 Celsius, which, when we convert into Kelvin, will give us 323 Kelvin. And it says, what is the new pressure? So P2 will be our value for X. So let's go ahead and plug and chug. P1 is 570 divided by T1, which is 300. And that's going to equal P2, which we'll call X, divided by T2, which is 323. Now to solve this problem, we'll cross multiply to find X. And when you plug this into your calculator, you're going to get the P2 is 613.7 torr. So again, plugging and chugging. The only part of this that should be remotely difficult is identifying what the pressure and what the temperature is. But we know that degrees Celsius is temperature, and torr, you will learn, is pressure. All right, finally the combined gas law. We can take Boyles and Gay-Lussac's law and combine them into one handy-dandy gas law. And that is called the combined gas law. So we get P1 times V1 over T1 equals P2 times V2 over T2. Now the best part of this law is it's the only one you really have to memorize, right? Because it contains both the ones we previously used. So if the problem only gives you pressures and volume, then temperature is remaining constant, and so we can just eliminate it from our equation. If you're given pressure and temperature, then volume must be remaining constant, so we can eliminate it from the equation. Right? Now we're going to use this law when multiple conditions are changing on a sample of gas at once. So here's an example. Now when you look at these problems, they're going to be super complex looking, so you have to make sure you go through and label your variables. So it says a container holds 0.046 liters of a gas. So I'm just going to go ahead and write V1 equals 0.046 liters. And it tells me that the pressure of that sample, we'll call that P1, is equal to 1.30 atmospheres. Now it also tells us that the temperature of that sample is 278 Kelvin. Then it says if the container is dropped into a lake to a depth at which the pressure is 1.52 atmospheres, so there's our different pressure, so P2 is 1.52 atmospheres, and the temperature is 275 K, so our new temperature is 275 Kelvin. What's the new volume? So our new volume will be X. So in this case, we're going to need the whole equation. So the equation again is P1 V1 over T1 equals P2 times V2 over T2. So now that we've labeled our variables, it's rather easy to plug them in. So P1 is 1.30 times V1, which is 0.046, divided by T1, which is 278. And that equals P2, which is 1.52, times V2, which is X, over T2, which is 275. So again, in order to solve for X, we're going to cross multiply. So 275 times 1.3 times 0.046 divided by 278 times 1.52 equals, I get 0.03889 liters. And that makes sense. The pressure only increased by a little, the temperature only decreased by a little, so the volume only changed by a little. All right, now here is a qualitative example. This comes from an SOL exam. It said in the picture below, both balloons contain the same number of moles of gas. That means they both have the same amount of gas inside of them, but one is much bigger than the other. It says give two possible differences between environment 1 and environment 2 and explain how each difference could cause the balloon to have a different volume. So we see in environment 2, balloon B is bigger. So what increases the volume of a container? Well, I know that if we increase the temperature, that's going to increase the volume of the gas in the balloon. So I know that environment 2 is going to be hotter than environment 1. Now let's look at another difference. So we've only talked about temperature and pressure here. So since we've already said that this environment 2 is hot and environment 1 is that must be colder, let's think about pressure. So if they have the same amount of gas inside of them, if balloon A is smaller, that means there must be more exterior pressure pushing in on it, right? So environment 2 must be at a lower pressure. And there are our two conditions. Finally, use kinetic molecular theory to describe what happens when a can of hairspray is thrown onto a fire. So we know the can is going to explode. I'm sure that some of the young males have tried this in their lifetime. If you haven't, don't. All right, so when the can's going to explode, but we need to use kinetic molecular theory to explain why the can explodes. So I know that once we throw the can onto the fire, the temperature inside the can will increase. It's generally what happens when you throw something onto a fire, right? That means you're going to have increased pressure inside the can. Now, you're going to have increased pressure because the particles will be moving faster. Right? So, particles moving faster. Now, if the pressure inside the can builds up enough, the pressure will be stronger than the walls of the can, and the can will burst, and you will get your explosion. So whenever we're asked to explain something using kinetic molecular theory, you have to talk about the motion of the particles and how changing different factors. That is it for discussion 8.1, unit 8, officially half done. This is a longer video. I appreciate your patience. I've just been trying to go through it slowly and clearly. Hopefully I succeeded. If you have any questions, please bring them to class, and I'll be happy to answer them.